Well, let's continue where we left off yesterday, which was looking at insertion. So insert root comma number. And this had to return a pointer to a tree node. So you want to insert, say, 15. And what it should do is give you something like this. And we looked at an iterative way to do that yesterday, right? So you start here and you basically move down, and when you get to a leaf node, you have to remember how you got there, right? Which node you had previously visited and whether you went to the left or the right, and then you said the left or right child equal to your new node. If you do this recursively, it's a little easier. So we can make a new node with our data in it. And if the root of our tree is null, we just return this new node. And we're going from an empty tree to a tree containing a single node, which is the node containing this number that we're trying to insert. So if the root's null, just make a new node, return it. Otherwise, if our number is smaller than the root, so the root does exist, if our number is smaller than the root, what we really want to do is insert into the left subtree. Right, so we can say insert root left number. And that will take whatever is on the left subtree, single node, big, huge, fluffy tree, and it'll insert our number into it. And this insert will return the possibly new root of this left subtree. So we just say root arrow left equals this. And then we just return the root of the new tree, which is just going to be the same as the original root, because we haven't changed that. Otherwise, our number is bigger than the root data. So do the same thing on the right. And there's no real special cases here except the base case where the root's null.
What if the number is already in the tree?
Don't call insert if the number's already in there.
So search first.
So search first, yeah.
You would just say if it's none of these three, then it must be the tree. Or I guess it might be null. Oh yeah, because if it's
Well, no, because you have null if it's greater than or if it's less than. So the only other possibility.
So if we made this an if, right, if root data was less than num, do this thing and return, then we'd have an extra case at the end, which would be neither of these was true, so it must have been matching the root data.
What exactly would you return? Just the root?
So you'd return the root, but you've got a bit of a potential problem. No, I think that would work. You return the root, and as you come back up the recursion, I think you'll just keep returning the thing that you were given. I don't think it'll change anything. But this is an interesting algorithm to unwind, right, and follow the call frames. Because if your tree is something like this, right? And you want to insert 19. Well, the first thing you're going to do is say 19 is smaller than 20. Let's insert 19 into here. And take the new tree and hang it off of this. And to insert 19 into here, we're going to say, okay, let's insert 19 into this right subtree. And to do that, we're going to say 19 is bigger than 15, so let's insert a 19 into here. And 19 is bigger than 17, so let's insert a 19 into here. And 19 is bigger than 18, so we're going to say let's insert into this tree. And the tree is null, so we'll create a node 19 and return that as the value from insert. And when we said insert into the right subtree, we're going to take root, which was 17 right, or 18 right, and set that equal to here. But now we're going to start popping up from all of our recursive calls, and each of our recursive calls said root arrow right equals or root arrow left equals the result of insert. So when we were inserting into here, we created this new subtree, and now 17's right child is this. And when we pop back from that, we finish the insert into this purple tree with 15 at the root, and now 15's right is going to be this, and so on.
What's the actual value of the pointers changing?
The actual, the only, it only changes the null. The only time that we actually return something other than the root that we were passed was in this case right here. But the effect is that, you know, this kind of trickles up, and when we're done, we've got our new tree. Yeah, yeah. But that's where actually everything happens. Right, that's the only time that we actually make a change to the tree. Yeah. But again, it's one of those that will drive you crazy if you think about it too deeply. But if you think about it sort of in a more touchy-feely way, it suddenly makes sense.
Well, I think of recursion, think of how those building trains build themselves up. Because they take a block, like stick it in them, and then move up.
Right.
Take a block,
Right.
and so they build up.
Yeah, yeah.
I keep thinking of like a small machine moving down, doing a thing, moving down.
Mm-hmm. That's a cool analogy. All right, so I did not post an ODP because I didn't know if we were going to have class today, so I will post it tomorrow. So let me talk about what this ODP is going to be. This is going to be a piece of the delete routine. So remember, when you've got a tree and you want to delete from the root, so let's say we want to delete 20. So our rule was going to be to delete the root. So to delete root. Find the largest node in the left subtree. And that's what your ODP is going to do. I'm going to give you a binary tree, the root of a binary tree, and ask you to find the largest node in the left subtree and just return that integer value. So in this case, the largest node would be 19, right? So how do we do this? Well, there's some edge cases. So if there's no left subtree, but I'm not going to give you a case where there's no left subtree. There will always be something on the left other than null for the ODP. But for the sake of the delete algorithm, right, first you have to check if there is a left subtree. If there isn't, then deleting the root is a totally different operation. You basically remove the root and you take the right child of the root and that becomes the new root. So if there's nothing to the left and you want to delete the root, you just replace the root with, you just call the root whatever the right child is. But we're going to assume there is something on the left other than null. And so to find the largest thing, basically move right. So start with root arrow left. And this is not null. And move right as far as possible. So we're basically working with this subtree, and we start off right here at the 10 and we just keep moving to the right until we can't move any further. The last node that we got to, that's the value you're going to return. And that's always going to be the largest, because if there was something larger, it would have to be to the right of that last node. So start with the left child. And while it has something on the right other than null, go ahead and move down. And then you should just be able to return temp data. So we start off with temp. Temp right is not null, so we set temp to temp right. Temp right is not null, so we set temp to temp right. Temp right is null, we kick out of our while loop, we return temp data, that's your 19. So the ODP is going to be pretty straightforward. It's moving through the tree and making some observations, and there's not a lot of housekeeping to keep track of. But when we move to actually wanting to delete from the tree for PA4, you got to do some more housekeeping here. Because when we do our deletion, here's what's going to happen. We're going to move all the way down until we find this 19. We're going to take this node and put it at the root. But 19 may have stuff on its left, right? It may have a whole subtree on the left. So the node that we were at before we got to 19, that's going to adopt this tree as its right child. So we're going to have to do the previous current thing to remember as we're moving through the tree what the prior node was. Because once we get here, we have lost some information. We need to know what the prior node was. So ODP, that will work, but let's look at the more general case. So let's start with temp. And there's going to be some edge cases here, but we can do something like this. So while the right child is not null, save the current node in previous. move down to the right. And then when we're done, what we should have is previous was the node that we came from. Temp is the largest node. All right, so what do we need to do here? We need to do a few things. We need the previous node to adopt temp's left child as its new right child. In other words, we need to take this node and connect it up to here. So something like previous right equals temp left. So adopt the largest node's left child. So that's going to take this subtree, put it up on 15. We're okay doing that. We're destroying the old value of previous right, right? We're overwriting that, but previous right was pointing to temp, and we've already got something, a variable named temp, that's giving us this node, so that's okay. So we can definitely do this first. And then we need to change 19 so that its left child is whatever root had on the left. In other words, we want to move this node up to the root. So we're going to do temp left equals whatever root had on the left. And then temp right is whatever root had on the right. So let's do that more carefully. And let's just throw some things over here to make sure we don't lose them. So here's our root. We're going to march through until we get down to a 19. This is going to be temp. And 15 is going to be previous. All right, so previous right is going to be temp left. So this is going to become the right child of the 15. And then temp left is going to become whatever root left was. So this node is basically going to point over here on its left, and temp right equals root right. This is going to point over here on its right. And then we can free root. So this will go away. And then we return temp as the root of the new tree. And so here's our tree. 19's at the root. Everything over here is smaller. Everything over here is greater. And the children of 19 are still adopted by the right of 15. Yeah?
Alternatively, could you change the data of root to equal temp's data and then free temp in the end?
You can, but I don't want you to do that. The idea is that the data itself might be something more than just an integer. It might be a linked list or a big long thing. So I want you to actually practice moving the nodes and the things they point to. This part is not recursive. This part's going to be, it's not really, well, it's a loop to get down to find that largest node, and then it's some statements to move around the pointers. So this part of delete is not recursive, okay? But this is strictly deleting the root.
So much to just do.
Yeah.
It's like if you want to delete any node, you can just stick it next to a search function. You'll just delete the root, but find the thing and then check.
Yes, and then you have to pop back up and make sure that everything's pointing where it should. So the whole delete function, most of it will be recursive, but there'll be one piece where we're at the node we want to actually delete, and that's the root of a subtree. That's where we're going to have to do this. And there's still some edge cases in here that we haven't addressed. So one possible edge case, say again? Root left is null. And there's nothing over here, so we can't find the largest thing in the left subtree because there is no left subtree. So the formula for deleting, the algorithm for deleting there is simply change the root to be whatever the right child of the root is. So root equals root, arrow right, and return root. That's redundant code. We could have just said return root arrow right. Doing this assignment really does nothing for us, but it's documentation. Oh yeah, so root equals root arrow right, so temp equals root, free temp, thanks. Yeah, he saved me from leaking my memory. So free the root and just return the thing that the root was pointing to on the right. The other edge case, possibly, is when you only have one thing on the left. Because our algorithm for finding the largest thing in the left subtree is the following: set temp equal to root arrow left. So this is temp. And then, well, temp arrow right is not null. Well, temp arrow right is null right away, so we're going to kick out, but we've never set previous, right? There's nothing available to adopt this thing's left child. And this could have, did I really put a 30 over there? That should be a 10.
Before you have the while loop,
If I set previous to the root, then I'm going to have this thing adopt the 8 and the 6, but I'm going to be getting rid of this thing.
but then you have this your new roots left child to.
Oh, I see, because you guys put 10 up on the 20.
Yeah.
You're getting rid of the 20 out.
Right, so we wanted the predecessor of temp to adopt all of this stuff, but the only predecessor of temp is the node that we're actually deleting. So this is actually an edge case.
So change temp right to root.
So yeah, so temp equals root arrow left. I know. So this is not null. And this while loop's normally going to go through until temp arrow right is null. But if the initial temp arrow right is null, that's an edge case. Well, how do we get rid of the 20? We're simply going to take this 10 and make that the new root. So we don't need to do anything with its left children. It will keep its left children, right? So all we have to do is say temp arrow right equals root arrow right. Right, that's that part of it. So this picks up those children and then free root and return temp. Otherwise, we go ahead and we do this usual march down to the right until we find a node with no right child and then adopt its left children and so on.
Sure that
Yes. So now we have a more complex. So this is the root delete. If there's no left child, do something special. If left child has no right child, do something special. Otherwise, do the usual algorithm where we move down to the right and we find the largest node, we pass on the children, and so on and so forth. So there's really three cases for deleting the root of a tree, and that's not the most general delete algorithm, right? Our general delete algorithm is actually recursive. So to delete from a rooted tree a particular number, we do the following. If root data do everything we've just been talking about, right? Delete the root. And return the new root of the tree, the root of the new tree. But if we're not trying to delete the node, right, we need to go into either the left or the right subtree. So if our number is less than root data, then we're going to delete from the left subtree, so root arrow left equals delete root arrow left comma num. And return our original root, because that didn't change. So if we've got our tree and we want to delete the 15, right, so delete 15. 15 is smaller than 20, so we're going to say delete 15 from this tree and take whatever tree you get back and make that the left child of 20. And when we try to delete 15 from this tree, we'll say 15 is bigger than 10. Let's delete 15 from this tree, take whatever tree we get back, make that the right child. When we try to delete 15 from this tree, we'll notice that 15 is the root, and we'll do our algorithm we've been talking about to delete the root. That would put a 19 up here and do some other stuff. And then we would return this tree from that delete, and our previous call to delete will say this thing's right child should be that new tree. And so we move that up in place and we pop back up our recursion. So if number is bigger than root data, do the same thing on the right. You don't if you know that yeah, you don't. So this is kind of assuming that the data is found in the tree. Yeah, we need a null case also, but we should.
If you do the search and the tree's empty, it's kind of
Yeah.
Yeah, so it's not in the tree. So let's just say num must be in the tree. If it wasn't in the tree, it'll eventually get to a point where root is null, and then it'll throw up.
it'll try to access it.
Yeah.
What do you call that?
If in the main program where it's doing calling all of these, if you search first and then you find what the value for search is, if it's equal to null, it couldn't find it, then you can just have an error message saying,
Right.
"Hey," and then don't delete the thing.
Yeah.
But if it does find it, it will have a value,
Mm-hmm.
because the tree must have something in it if it.
Right. Unless someone changes your tree while you're running this. That doesn't happen.
That's not possible, because two users trying to do something.
Correct.
No, two programs accessing the state.
Right. Well, but you don't necessarily know how this is being called. So you might have two processes chowing on the same locations in memory, and one of them is deleting something, and the other one wants to delete something, and already got started because it found it in the search, but meanwhile it got deleted. And so when we do multi-threaded programming in 223, we'll have lots of fun with that, because you get into all kinds of good things. Yeah. All right. That's the basic gist of delete. So think about that, and we can go over it in more detail tomorrow if we want. Otherwise, I'm going to talk about tries tomorrow and some other things related to trees. And then next week, I think we're going to talk about dynamic programming. And then week 9, we'll come back and maybe talk about balancing. But we got to do sorting, we got to do searching, we got to do heaps, and probably some other stuff. So we got lots of good stuff to talk about still.